Hello, precalculus class. Today we're going to look at the third method of solving a system of equation using matrices, something called finding the inverse of a matrix and using it with multiplication. So here's your warm-up, and go ahead and pause the video, answer these questions, and then we'll go over the answers. Okay, here are your answers. The first one, when you do A minus B, you want to make sure that they match in dimension. So they're both 2 by 3s, and here is your result right here. The next question is a scalar multiplication. So you're just multiplying each element of C times -3. The next one I'm going to wait on. Then it asks, can you add A and C? And the answer is no. A is a 2 by 3 and C is a 1 by 3. So they're not the same dimensions. Next it asks, can you multiply A times C? So A, like we said, is a 2 by 3. C is 1 row by 3 columns. So when I look for that inner match, which I must have, I don't have it. So the answer is no, they cannot be multiplied together. So now let's go and do C times D. So C and D, C is a 1 by 3. I rewrote it. D is a 3 by 3. So we have an inner match, and we know the result will be the outer dimensions, will be a 1 row by 3 columns. So here's your answer, 30, -2, 7. And just to help you out, I have the work down here. When you haven't multiplied in a bit, you get rusty. The key is you are taking each row times each column. So 1 times 6 is 6, 0 times 4 is 0, 3 times 8 is 24, which makes the 30. Likewise, row by column, here's the greens, and row by column, here's the yellows. And that's how we get our answer, which is a 1 row by 3 columns. All right, so on this first slide, we're going to learn about something called the identity matrix. An identity matrix is just that reduced row echelon form kind of coefficient part where you've got ones on the diagonals, or the kind of the main down diagonal, and zeros everywhere else. So you only have this in a square matrix. And if it was a 4 by 4, you'd have 4 ones and 3 zeros here and 3 zeros here. Oh, I'm sorry, it's actually more than that. It's 6 zeros in each side. And then that's called an identity matrix. Now, the positive thing about an identity matrix, and you're going to test this out here, is if I multiply some matrix times the identity that I can multiply it by, looking at your inner dimensions. So for instance, your A matrix is 2 by 3. So that means we need to multiply it by its 3 by 3 identity to have that inner match. Likewise, if we're going to do something times A, so A, of course, is 2 by 3 again. So I have to have that inner match. So that means I'll use the identity that's 2 by 2. And if I'm going to do B matrix, which is 3 by 2, it's got to be multiplied by the 2 by 2 identity. So what happens when you multiply by the identity matrix is pretty neat. It's an identity. It's like adding 0 or multiplying by 1. It does not change the original matrix. Whether you, and this is commutative, so whether you put the identity in B here first, or you put the identity in part C here second, you will always get the original matrix. So go ahead and try that out, and then I will show you some results as well. So here is the results. So when I do the A matrix here, 2 by 3 times the 3 by 3 identity matrix, you end up back with the A matrix. So it equals A. In the second example, it actually should say I2, identity 2 by 2 times A. We're switching the order. So here's your 2 by 2 times your 2 by 3. So your result is, let's just write that out so you can see it. So your result is a 2 by 3, which is the one you started with. Once again, A. And the last example, which is your B matrix times your identity 2. So this is a 3 by 2 times a 2 by 2 So your result is a 3 by 2, which is B. So that leads us to properties of identity, which says if A is an m by n matrix, then the multiplication of that matrix by an identity matrix will return A, or an m by n square matrix. This will help us when we go to solve a system of equations. The last special matrix you need to know about is something called the zero matrix. This can be any dimensions, but it is filled with zeros. And when you add the zero matrix to a matching dimension, any other matrix, it does not change its value and it returns the matrix you started with, just like the addition property of zero. Okay, so now for us to talk about the inverse of a matrix. So if we have a square n by n matrix, there exists an inverse matrix. And the way you find that is it is the matrix that when multiplied by the original one will get you the identity matrix. So the key is, and it doesn't matter the order. Remember, multiplication is not commutative in normal times, but when you are multiplying a matrix by its inverse, you get the identity out. So the first thing we're just going to show is that that property works. So here I have matrix A, and here I have the inverse of matrix A, which I'll show you how to find in a few minutes. And we're going to multiply these together. So remember, it's row times column. And if this is 2 by 2 and this is 2 by 2, we've got the inner match, and my result will also be 2 by 2. So let's give us our space. So -3 times -1 is 3. -1 times 2 is -2. Likewise, we'll do that same top row times the second column. So we end up with a 3/2. And then -1 times 3/2 is -3/2. And then the bottom row times the first column, you have a -4 plus a 4. I hope you notice that these both become zeros, and they better because we're looking for the identity out. And then we have the last row times the last column. So 4 times -1/2 is -2. 2 times 3/2 is +3. So when we simplify this, we end up with a 1, a 0, a 0, and a 1, which is your identity 2 by 2 matrix. So that is showing you that multiplying these two together will get you back to the identity matrix. So now we need to find out how we can find the inverse of a matrix. The key is you're going to take the matrix you have and augment it with the identity matrix of the same size. And you're going to apply your row operation rules to the whole thing in order to get the original matrix A into reduced row echelon form. So in a 2 by 2, remember that looks like this. 1's on the diagonal and 0's everywhere else. On a 3 by 3, it's 1's on the diagonal and 0's everywhere else. Now, as you apply those rules, changes are going to happen to the side with the identity. As you get to this new form on the left, the right-hand side will become your inverse matrix. All right, let's go ahead and do an example. The first thing we'll do is set up our augmented matrix with the identity on the right-hand side. Then I need to get 1 in the top left corner, so I think I'll just divide by -2. So row 1 equals -1/2 times row 1. And let's see what happens. You end up with a 1, and then 2 divided by, or times -1/2 is a -1. And 1 divided by that is, or times -1/2 is -1/2, and 0 doesn't change. And row 2 does not change. Okay, so next I need a 0 right here. So we're going to take row 2 and replace it with 9 times row 1 added to row 2. And the top row does not change all the way across. But the bottom row, we have 9 times 1 added is a 0. Negative 9 plus 8 is a negative 1. Negative 9 halves plus 0 is negative 9 halves. 9 times 0 is 0 plus 1 is 1. So we are getting closer. The next thing we need to do as we keep moving along is we have to get a 1 here. So it's right now a negative 1. So I'm just going to multiply the whole row. Row 2 is going to be negative 1 times row 2. Just change the sign of the whole row. I'll rewrite the top row. And then here we change the sign. Okay, and last step is to get a 0 up top right here. So to do that, I can just add. This is quite nice. I'm going to say row 1 equals row 1 plus row 2. Note when you add a 0 to it, it doesn't change. So this is still going to be the way it is. The bottom row is done because we're not changing row 2. And when you add 1 to negative 1, you get a 0. 9 halves minus 1 half is 8 halves, which is 4. And negative 1 plus 0 is negative 1. That is the inverse of A. And remember the inverse notation. I didn't bring this up before, but it's like to the negative 1 power is how we represent an inverse. Remember, if you have function x, this is your inverse function. So it's the same notation you've seen before. And it's 4, 9 halves, negative 1, negative 1. Now we could test that. And if we wanted to, we would make sure this times the original matrix B is the identity matrix. Oh, it's called matrix B. This is the inverse of matrix B. I apologize for my naming. All right, here's another example that I would like you to go through finding an inverse matrix, but you're going to find it has no inverse, that this is a singular matrix. So go ahead and pause the video and try it and see what happens. Okay, take a look. I start going through the row operations to get the identity on the left, and I end up with this column right here with a 0, 0. There's no way I can all of a sudden make that a 1. So I am done, and I can conclude that matrix A here is singular, which means it has no inverse. Another way to double check whether a matrix is singular or not is to find the determinant. So I'm going to quickly find the determinant of matrix A and show you that you end up with 4 minus 4 or 0. If the determinant equals 0, then we know that no inverse exists and it is singular. We need a non-singular matrix in order to find an inverse. Okay, in this final example of finding an inverse, I have a 3 by 3 that I would like you to try to do by hand. And then when you are done, this is going to make you a little bit angry. I'm going to show you that you can do this with your calculator. So set it up, pause the video, and then you can see my work when it's unpaused. Okay, so this is quite a long process, but if you can follow it through, what was nice is we already started with a 1 and a 0 in the first two positions that we needed. So all we needed to do is make this 2 into a 0 by this rule. And you apply it all the way through. Then I needed this to be a 1, so I just multiplied the second row by negative 1, and that's what we've got here. Then we need to get zeros here and here. So here's the rules that we used. Row 3 was negative 4 times row 2 plus row 3 to get rid of that. And row 1, I just added the 2 together, and that makes a 0. So you apply it all the way across. The last part is where you start bringing in fractions, because to get rid of this 9, I have to multiply by 1/9, and that creates this. Then our final steps is to get zeros here and here, and we do that by taking row 1 is row 3 plus row 1, because that makes a 0. And 3 times 1 is 3 plus negative 3 is a 0 here. So in this final step, your row 1 and 2 change. And here is your inverse of matrix A. And of course, I simplify the fractions where I need to. And there you have it. Now, if you want to check your work, you've learned about the matrix menu. So you're going to go in and you're going to enter our original matrix A into the calculator. And then you're going to get out and name matrix A and then use the -1 function or inverse key, which you'll see there is write x to the -1, 4 down on the left, and it's the white key. So no second function needed. It just says x -1. You hit enter on that. It will produce this inverse matrix in decimal. And if you want at that point, while it's still showing on the screen, hit math frac, and it will turn it into these fractions. Go ahead and try that. And if you have any trouble at all with it, I will show you during one of our Google Meets. That's it for the lessons. Go ahead and try the homework.